Welcome to 2.6 Special Functions. Today we're going to identify and graph step, constant, identity, absolute value, and piecewise functions. So first up, some vocab. A step function. If the graph is not linear, it consists of line segments or rays. So right here we have a step function. An open dot, or a dot, means that the point is included on the graph. The circle, the open dot, means that the point is not included on the graph. So notice that it's just a bunch of segments, but the same frequency and stuff like that. So the idea is it's just a step, it's going up and up and up, or down and down and down. Okay, example 1, our step function, labor costs at the Fix-It auto repair shop are $60 per hour, or any fraction thereof. So draw a graph that represents the situation. So we're going to start with the total labor charge must be a multiple of 60. So the graph will be the graph of a step function. If the time spent on the labor is greater than 0 hours, but less than or equal to 1 hour, then the labor cost is $60. If the time is greater than 1 hour, but less than or equal to 2 hours, then the labor cost is $120, and so on. So we're going to use the pattern of times and costs to make the table, where x is the number of hours of labor, and c of x is the total labor cost. Then we're going to draw the graph. So here is the idea. From 0 to 1, it's $60. From 1 to 2, it's $120. From 2 to 3 is $180, so on and so forth. We're going to graph this. We're going to go up by 60s on the y-axis, and then we're going to go by 1 hour on the x-axis. So it's never equal to the smaller one, because we're not going to do a cost of 0 hours. Right? At 1 hour, it's going to be the lower price, not the higher one. So that's why the open circle's first. We're closed on the second part because that's where it hits the hour. And if it goes above, we just go up to the next step. So since the shop rounds any fraction of an hour up to the next whole number, each segment of the graph has a circle at the left endpoint and a dot at the right endpoint. Our next type is a constant function. When m is 0, the slope is 0, the value of the function is f of x equals b for every x value. So our constant function here, f of x equals 3, for every value of x, f of x is 3. The graph is a horizontal line. So here, -2, -0.5, 0, 1/3. It does not matter what x is. The y is 3, so our graph is a horizontal line like this. The identity function, f of x equals x, where the function does not change the value. So here is the example. This is another case of slope-intercept form where m is 1, b is 0. This is the function f of x equals x. The graph is the line through the origin where slope is 1. Since the function does not change the input, f of x equals x is called the identity function. We have absolute value function, f of x equals the absolute value of x. This is another special function where no matter what, your y value is positive because the absolute value is the distance from 0. So it makes a v sign. Absolute value function can be written as f of x equals negative x if x is less than 0, and positive x if x is greater than or equal to 0. A piecewise function is just a function that is written using 2 or more expressions. So we're going to do the absolute value of functions. We're going to graph the absolute value of x plus 1, and we're going to graph the absolute value of x minus 2 on the same coordinate planes. We're going to determine the similarities and differences in the two graphs. So we're going to first find the several ordered pairs for each function. So in x, the absolute value of x plus 1, we're going to use the values for both of our graphs. We're going to use -2, -1, 0, 1, and 2. We're going to substitute it in. So for the absolute value of x plus 1, we get -2, 3, -1, 2, 0, 1, 1, 2, 2, and 3. For absolute value of x minus 2, we get -2, 0, -1, -1, 0, -2, 1, -1, 2, 0. So our graphs looks like this. Our absolute value of x plus 1 is above, absolute value of x minus 2 is below. The domain of each function is all real numbers, as it goes as far to the left and to the right as possible. The range of the value of absolute value of x plus 1 is y so that y is greater than or equal to 1. The range of g of x is for absolute value of x minus 2 is y so that all y's are greater than or equal to negative 2. The graphs have the same shape but different y-intercepts. The graph of absolute value of x minus 2 is the graph of the absolute value of x plus 1 just translated down 3 units. Our example of piecewise functions, we're going to graph the function of x equals either x minus 4 if x is less than 2 and 1 if x is greater than 2. So we're going to graph the linear function f of x equals x minus 4 for x is less than 2. Since 2 does not satisfy this inequality, we're going to stop with an open circle at 2, negative 2. Graph the constant function f of x equals 1 for x is greater than or equal to 2. Since 2 does satisfy the inequality, we're going to begin with a closed circle at 2, 1. We're going to draw a horizontal ray to the right. The function is defined for all values of x, so the domain is all real numbers. The values of that are y-coordinates of points on the graph are 1 and all real numbers less than negative 2 for the range. So the domain is all real numbers, and the range is y is less than negative 2 or y equals 1. Alright, so let's look at all these functions again. You got the step function, it's just horizontal segments and rays. You got the constant function, which is a horizontal line. You got the absolute value function, which is a V-shape. You got the piecewise function, which is different rays, segments, and curves. Finally, we're going to identify a function. So we're going to determine whether each graph represents a step function, a constant function, or an absolute value function, or a piecewise function. So the first one, A. The graph has multiple horizontal segments. It therefore represents a step function. Part B, the graph is a horizontal line. It represents a constant function. All right, that's it for the linear relations and functions. Good luck on the practice.